Okay, so welcome back. So what we're trying to do now in 910 is find a method for the power series representations of functions that does not include this crazy backdoor method where we just note a peculiarity about a particular the geometric series in particular, and then kind of luckily are able to integrate and produce these formulas. We want a general way to do it. And it turns out the way we learned to produce those polynomials back in 9.7 is the way it needs to be done. Okay. Taylor and Maclaurin series. So it's in theorem 9.2 that we have this fact, 9.22 actually. If f is represented by a power series, so if this function has a power series representation, for all x in some open interval I, containing the center C, then its coefficients, a sub n, must be this formula that we found when we were dealing with the polynomials, right? So f of n of c all over n factorial. And why is that? Well, it's pretty straightforward. If you have, supposing you have a polynomial, um, a power series representation, we can take its derivative over and over and over, and then equate the function and its derivative, and this formula will develop from the sort of system of equations that results. So note, if we have a function and its power series representation, it'll have an equality to it like this function on one side and then the representation on the other. And I'll just use centered at 0 for the sake of sanity. Right, and then we could continually take its derivative. So there are some sort of restrictions, I suppose. Okay, so anyways, taking derivatives, I get a1x plus a2x plus 3a3x squared plus dot 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 f double prime of x 2a sub 2 plus 3a sub 3, or rather 3 times 2a sub 3 x plus 4 times 3, sorry, let's see that, 4 times 3a sub 4 x squared plus dot dot dot. And continuing on and on, the nth derivative at x will equal, n factorial times a sub n plus 1 factorial times a sub n plus 1 times x plus dot dot dot. So note, second derivative puts 2 factorial here. The next term was n plus 1 factorial, so 3 times 2 is really 3 factorial, so that would be n plus 1 factorial, and so on. If you evaluate these at 0, you get kind of these coefficients, right? So evaluating at 0, I note f of 0 equals a sub 0, f prime of 0 equals, and of course you put in 0, and this, sorry, should be a sub 1 plus 2a sub 2x. You plug in 0 into this expression, everything goes away except that first term. So this would be a sub 1. F double prime of 0 is 2a sub 2. And of course, in solving for that coefficient, then a sub 2 must be f double prime of 0 all over 2. 2 is the same as 2 factorial. F triple prime of 0, I don't have it written, but it would be 3 factorial a sub 3. And in other words, a sub 3 is going to be the third derivative evaluated at 0 divided by 3 factorial. and in general, then a sub n is equal to exactly what we were saying. It was equal in the proof, or in the theorem, sorry. So in general, we'll have f, the nth derivative evaluated at 0 equaling n factorial times a sub n, which implies a sub n equals the nth derivative evaluated at 0 all over a sub n. Okay, so if a function does have this representation, it has to have that form that we saw with the Taylor and polynomial, the Taylor and Maclaurin polynomials. So we haven't said when does it absolutely have to have that form. So saying that all functions have these representations may not necessarily be true. So anyways, getting back to reality here, then we have our Taylor and Maclaurin series representations for functions. And they are exactly what we saw before. I'll write down the Taylor version. Okay. Which of course is just f of c plus f prime of c times x minus c plus f double prime of c all over 2 factorial times x minus c squared plus f triple prime of c all over 3 factorial times x minus c cubed plus on and on and on. Okay, so it's Taylor when not centered at 0, and Maclaurin when centered at 0. Okay, so even before we talk about whether or not these things will work as representations, we'll just build the Taylor series representations. Okay, so number 9. We are trying to find the Taylor series for a particular thing. And actually, this will be a Maclaurin. But let's look at it. So f of x equals sine of 3x. And so this is find the Maclaurin series. In other words, c equals 0. Okay. So the way it works is basically find the derivatives, evaluate the derivatives, and then plop it all into your formula. Okay. If you get ambitious, do the power series representation for the series. Usually on a test, and because I know not everybody's going to go on in math, I just let you write out the first 5 or 6 terms, and that's good enough. But anyways, let's go at it. So I got f of x is sine. I'm going to go to probably the 5th derivative here. And that should give me a pretty good feel for how the thing is working. And then I can pick out a pattern and go to my summation notation if I want. Okay. So remember chain rules here. Cosine 3x times 3. Okay. Negative 3 squared sine 3x. Negative 3 cubed cosine 3x. 3 to the 4th sine 3x. And then 3 to the 5th cosine 3x, evaluating it at the center. Remember, sine of 0 is 0, cosine of 0 is 1. So we get 0, 3, 0, negative 3 cubed, 0, 3 to the 5th. Okay. So it looks like my power series representation for sine of 3x is going to be, let's just write it with sort of fill in the blanks again, like I did with the polynomial version of this problem. Okay, so what am I doing? I got 0, 3, 0, negative 3 cubed, 0, 3 to the 5th. I want to rewrite that in summation notation. So I'm going the series. Looks like we have some alternating terms. The exponent on our remaining polynomial terms, x, x cubed, etc., will be 1, 3, 5. So the sequence 1, 3, 5, etc. represents our exponents, as well as the factorials on the denominator. So the first one's 1 factorial, then 3 factorial, then 5 factorial. There's also a negative thingamajig in there, so I have to have a negative 1 representing to some power when it's, so we'll have x to some power, negative 1 to some power, all over this thing, and this thing will be the same, factorial, and I have to figure out n equals what to infinity. So it's kind of like a big fill-in-the-blank type problem. So if you pick your formula for this to be, and this is an arithmetic sequence, so the formula a sub n should be a sub 1 plus, depending on where you start, n minus 1 times the difference between these two, so 2. Or if you would rather just starting at 1 as opposed to 0, you could put n in there. So it would be, no, that won't work, right? So sorry, the standard formula is a sub n equals a sub 1 plus n minus 1 times d. The problem is I want my series, I know I want my series to start at 0. Okay, so this formula might not be the formula I want, but let's see what it is, right? So a sub n equals 1 plus n minus 1 times d, the difference between two consecutive values, right, which is always 2. So I'd have a sub n equals 1 plus 2n minus 2, which equals 2n minus 1. So the problem is if I start at 0, my first term in the sequence would be negative 1. So I can't start there. I have to shift it over by 1. And in that case, this formula won't work, right? So I actually want to use 2n plus 1 for my formula. So 2n plus 1, 2n plus 1 up here. And then to get the first term to be positive, I'll just use n. So I want to start at 0 because traditionally the Maclaurin series for sine starts at 0, and I know that from experience. You probably don't. The truth is it's non-unique. You could start at n equals 1 and then use that other equation, the 2n minus 1, right? So that would give me 2 minus 1 is 1 for the first term. And oh, I'm missing a 3, right? So you'd have to have this 3 to the power of 2n plus 1 as well. Sorry about that. Yeah. So that'll be something you'll have to work on and get through in the notes. Hopefully I can do maybe one or more examples later on here. I don't think I'll have time though. No. All right, so there's that. You know, it may be more clear if you get rid of the 0 parts of that polynomial. So it's really 3x minus 3 cubed all over 3 factorial x cubed plus 3 to the 5th all over 5 factorial x to the 5th minus dot dot dot. And if you plug it in here, you can see your answer. But like I said, it's non-unique. If you wanted to start in your naivety at 1 instead, your negative 1 for the first term would have to be n plus 1 to make it positive. And then x to this power has to go 1, 3, 5, etc. And in that case, you need 2n minus 1. and that'll come from the formula for the arithmetic sequence that I derived above. All right, and then this would be 3 to the 2n minus 1 all over 2n minus 1 factorial. So it's non-unique, but like I said, it's tradition to start the Maclaurin series for sine at 0. So this is usually the formula thereafter. And hopefully that doesn't confuse you. But like I said on the test, I'm probably happy if you just put the first couple terms and leave it at that. Okay. What was I saying? Okay, that's fine. Okay, so anyways, I've been saying that these are the representations of the series, not necessarily, it's not necessarily always going to conform to the actual function, okay? Especially if you're dealing with piecewise functions and you center your Maclaurin in one piece of that piecewise function, your derivatives are going to be based off that one piece, not off the other pieces. So it probably, in all likelihood, will not conform to the other pieces unless the other pieces are, what they would normally be if it was a non-piecewise function. It's a weird sort of way. So, so you have to have this theorem 2.9.23. Which tells you when these things are actually going to conform to the original function. And it all goes back to that Taylor's remainder formula. Basically, if r sub n of x, the difference between the polynomial approximation and the actual function goes to 0 for all x in some interval I, then the Taylor series actually equals the function it's representing, equals the function it represents. Okay, so again, the issue is if you have some sort of weird piecewise function like this guy, which is sine of x in the middle, and then on the ends, maybe it's just y equals 1 and y equals -1. So f of x equals -1, and then sine of x, and then 1. Okay. If you build your Maclaurin polynomial centered at 0, your Maclaurin polynomial is going to conform to sine of x. So for x values over here, this thing will not work, okay? And in particular, the difference between the polynomial and the actual piecewise function are going to be off once we get out to these x values. Okay, so that's the primordial example that everybody always shows. Well, I assume everybody would show it. I don't know if they really do. Yeah, so anyways, we need to at least do this once, show that this works once. And the easy one is always using maybe proving that an exponential or the sine of x works. So we'll do it with sine of x. Okay, so example 2, we want to show that the Maclaurin series for sine of x converges to sine of x for all x. So show the Maclaurin series for sine of x is equal to sine of x for all x. Okay. So the example that we just did is kind of like sine of x. That's pretty much what our sine of x formula looks like. We just note the representation, the Maclaurin representation. What the heck is it? It's the series -1 to the n times x to the 2n plus 1 all over 2n plus 1 factorial from n equals 0 to infinity. Okay. Right. So what we want to show is that the limit of r sub n of x equals 0 as n goes to infinity. Okay. So we need to figure out what the heck r sub n of x is and work with that. So we note from I think it was 9.7, the absolute value of r sub n of x is equal to basically the next term in the polynomial, Maclaurin polynomial of degree n. So the next term in that polynomial would be, and it's an absolute value of it, so it would be sort of the nth derivative of the original function, but maximized on the particular interval. So max the absolute value of the n plus first derivative on some interval divided by n plus 1 times the absolute value of x minus c. In this case, c is 0, so we just have x to the n plus 1. Okay. So to work with this thing, the first topic, or the first thing we want to kind of eliminate is this numerator here. So we know that we can do this because the n plus first derivative of sine is going to be either, again, one of four things: negative sine, negative cosine, sine, or cosine, right? And then when you take the absolute value, you cut that down to just two possibilities. And then in particular, the maximum of those two possibilities is definitely less than 1. Okay? So we've done it. We've kind of eliminated this numerator term, and we can sort of re-envision this absolute value. So hence, we have the absolute value of r sub n of x being, and of course this is greater than or equal to 0, and then less than, and I shouldn't have said equals, I'm going to put that as a less than or equal to, we have r sub n of x then less than or equal to 1 all over n plus 1 times the absolute value of x to the n plus 1. In other words, absolute value of x to the n plus 1 all over n plus 1, and this should be factorial as well. Okay. Okay, so what? Well, I'm going to do a squeeze theorem on this term and this term in order to make this pan out for me, right? So if I could take the limit of this thing, it's going to, and it's equal to 0, and the limit of this thing is obviously equal to 0. It forces the limit of this thing to be 0. So let's note then the limit of that expression. And I kind of can't work with it as is, okay? So what I'm going to have to do is remember the nth term test for divergence. So note if, what was that? The divergent test, right? So if the limit as a sub n, as n goes to infinity of a sub n actually does not equal 0, then the series a sub n diverges. The way I want to use it, though, is if the series of a sub n converges, then the limit of a sub n equals 0. Okay, so I'm trying to show that if this equals, the limit of this is 0 and the limit of this is 0, it forces this limit to be 0, and then we can say that the Maclaurin series is equal to sine of x. Okay, so I'll have to consider then the series absolute value of x to the n plus 1 all over n plus 1 factorial. Okay? Because if I can show that's convergent, that'll imply that the limit of this is 0. Okay, so I use the ratio test. And I note what? Well, the limit of a sub n plus 1, which is absolute value of x to the n plus 2 all over n plus 2 factorial, times the reciprocal of this expression, so n plus 1 factorial all over the absolute value of x to the n plus 1, right? This will equal the limit of the absolute value of x times 1 all over n plus 2. And then if I factor out the absolute value of x, I just have the limit of 1 all over n plus 2, and that's L over infinity. So this is a big 0, and anything times 0 is 0. Our R value then from the ratio test is less than 1, and therefore it's convergent for any x. Hence, the series converges for any value of x. Okay. In other words, by the nth term test, it must be that the limit of the absolute value of x to the n plus 1 all over n plus 1 factorial is equal to 0. And then by the squeeze theorem, we kind of have what we were after. And we found that the limit of this is 0. Obviously, the limit of 0 is 0. Hence, by the squeeze theorem, the limit of r sub n of x is equal to 0. And so we can conclude that sine of x is equal to its Maclaurin series for all x. Okay, so that's sort of a taste of how that works. Let's look at some other topics in this section. So the binomial series, we have that. So the binomial series, well, the binomial expansion we have from basic algebra, I guess, and you can use Pascal's triangle to kind of figure it out, but we want to look at the binomial series for expressions like 1 plus x to any power of k, where k can be a rational number in addition to just an integer number. Okay, so the way we derive it is the same way as before. We just consider f of x equals 1 plus x to the k, and then just keep taking its derivative. Okay, so f prime of x is k times 1 plus x to the k minus 1. F double prime of x is k times k minus 1 times 1 plus x to the k minus 2. F triple prime of x is k times k minus 1 times k minus 2 times x plus 1 to the k minus 3, etc. And then our nth term derivative is going to be k times k minus 1 times k minus 2, all the way down to, what was this? This was the third. So all the way down to k minus n minus 1 times 1 plus x to the k minus n. Okay, let me just look at that real quick, make sure that's right. So this was 2, which n minus 1 is 2, so that's 2. 2 minus 1 is 1, so that was 1. So n minus 1 is the thing we're subtracting away there. When we evaluate these guys at our center 0, what do we get? F of 0 is 1. F prime of 0 is k. F double prime of 0 is k times k minus 1. F triple prime of 0 is k times k minus 1 times k minus 2. And then in general, the nth derivative evaluated at 0 is just going to be this thingamajigger. K times k minus 1 times k minus 2 all the way down to k minus n minus 1. And then we plop it into our formula. So we'll have this representation. What is it? 1 plus k times x plus k times k minus 1 all over 2 times x squared plus k times k minus 1 times k minus 2 all over 3 factorial x cubed plus et cetera, et cetera. Right? Okay. The book notes this thing will converge. Don't ask me how they know, but it converges on -1 to 1. Okay, okay. So they'll have you do some Taylor series expansions for some of these characters. For example, f of x equals 1 all over the square root of 1 minus x. Okay, so this is 1 minus x to the -1/2. In other words, we're doing a replacement of x with negative x, and then our k value is actually -1/2. Okay. So you can use this as a formula and just do a substitution into it. So our representation for this thing would be 1 plus -1/2 times -x plus -1/2 times -3/2. -1/2 minus 2/2 is -3/2 all over 2 times -x squared plus -1/2 times -3/2 times -5/2 all over 3 factorial times -x cubed, and it just goes on and on, right? You can make it look pretty and simplify it. That would be nice. Okay, let's move on. And what we're wanting to do is derive, we'll have a list of Taylor series that, if we played around with Taylor series a lot, we would kind of have the list encoded in our brains somewhere, but it's in the book in a big table. So after you've mastered all of chapter 9, you could probably just use the table for the series. So you do it via substitutions or taking derivatives, just like we did with the geometric series to produce the natural log series and to manipulate the original geometric series. So for instance, f of x equals e to the 6x. Okay? So in the tables, I look for e to the x, and I find that that thing is the sum of x to the n all over n factorial from n equals 0 to infinity. Okay? So in other words, 1 plus x squared over 2 plus x cubed over 3 factorial plus dot, dot, dot. So to find e to the 6x, what you do is just replace x wherever you see it with, guess what, 6x. And that'll do the job. So we'll have n equals 0 to infinity of 6x to the n all over n factorial. And so obviously we have a 1 plus 6x plus 6 squared x squared all over 2 factorial plus 6 cubed x cubed all over 3 factorial, etc. Okay, so pretty simple. Right. Something that I see done kind of in differential equations using multiplication and division of these things. So we have it's literal multiplication and literal division. So you would do long division where you set up your symbol and all that jazz. Let's just look at multiplication example where we're finding the first 4 non-zero terms. So here f of x equals e to the x sine x. And so we have e to the x is equal to, from above, 1 plus x squared over 2 plus x cubed over 3 factorial plus x to the 4th over 4 factorial. Okay. And then right below it, just like you did back in elementary school, you're going to multiply it by the Maclaurin series for sine of x, which in this case is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, etc. Okay. So how does this work? Well, you just literally do a distribution, okay, and then you combine like terms until you get the number of terms required, and here we want the first 4 terms. Okay, so I'll multiply through by x, distributing through here by x, you get x plus x squared plus x cubed all over 2 plus x to the 4th all over 3 factorial plus x to the 5th all over 4 factorial. And you just keep going until you get enough terms that you think are going to give you the 4 terms that we need. Distribute the negative x cubed over 3 factorial, so that's going to end up over here, right? So this, this times this gives me negative x cubed all over 3 factorial. And then, sorry, this times this gives me negative x to the 4th all over 3 factorial. And then this times this, negative x to the 5th all over 3 factorial times 2 factorial is going to be 12. Or you could just write 3 factorial times 2 factorial. Obviously, these guys are going to cancel out, so I'm going to need this 5th term to get the 4 terms I want. Anyways, this, this guy now multiplying through, I get x to the 5th all over 5 factorial. And then I think I have enough terms to cover my bases. So I have x, then plus x squared, and then finding common denominator and adding them together. This will be plus x cubed all over 3. These cancel out, and then these in my calculator I added them earlier, so it's, I know it's x to the 5th over 30 plus dot dot dot. So why would I do that? It's because if I'm looking for the Taylor or the Maclaurin series for this guy, I would have to do derivatives that involve the product rule all over the place. Okay, so my derivatives would get nastier and nastier, and it would become more and more difficult to pick off the coefficients. Okay, so that's the reason why you do it. And like I said, in differential equations, sometimes your teacher will have you do that. Okay. Okay, so finally then, one thing we could do with these, one application, is the approximation of integrals that we couldn't necessarily integrate. Right? And you may feel like you can integrate anything at this point, but that's not true at all. Seems like I've heard the vast majority of integrals you're not going to be able to do are simple substitution rules on and that sort of thing. So here's 63. You have the integral from 0 to 1 of e to the negative x cubed dx. You want to approximate this integral. Obviously, I can't do a substitution rule on it. There's no way. I want error less than 0.0001. Okie dokie. So first off, get the Maclaurin series for e to the negative x cubed. I recall that the Maclaurin series for e to the x is just 1 plus x squared over 2 plus x cubed over 3 factorial, etc. So e to the negative x cubed, you just do a substitution into this expression, and you get 1 minus x cubed plus x to the 6 all over 2 minus x to the 9 all over 3 factorial plus etc. Right? Okay, so I want to integrate this thing. So by the way, that's that. And then this thing equals the integral of 1 minus x cubed plus x to the 6 over 2 minus x to the 9th all over 3 factorial plus x to the, let's just get a couple more terms in case I need them for my approximation. I'll just go out to the next one. 6, 7, 8, 9, 10, 11, 12 all over 4 factorial dx. And then integrating term by term, I'll get x minus x to the 4th all over 4 plus x to the 7th all over 7 times 2 minus x to the 10th all over 10 times 3 factorial plus x to the 13 all over 13 times 4 factorial. And carrying on, I think I'm gonna need a couple more, maybe 1 or 2 more terms. x to the, this will be 16 all over 16 times 5 factorial plus x to the 19th all over 19 times 6 factorial, on and on. I have to evaluate from 0 to 1. So plugging 1 into that expression, I get the series 1 minus 1/4 plus 1 all over 7 times 2 minus 1 all over 10 times 3 factorial plus 1 all over 13 times 4 factorial minus 1 all over 16 times 5 factorial plus 1 all over 19 times 6 factorial, etc. And then minus this thing evaluated at 0 will just be 0. Okay, so I don't have to worry about that. Alrighty then. This is an alternating series, and we can use alternating series estimation theorem then to get our approximation. So then recall, and I'm going to assume that this thing converges. Okay, I'm not going to prove it, but recall, alternating series test said that s minus s sub n will be less than a sub n, or less than or equal to a sub n plus 1. Okay? So what that comes down to, what that'll boil down to, is kind of a trial and error, where you're inspecting this guy. If this guy is less than our error value, then you just add up everything before it. Okay, the s sub n will be everything. This will be a sub n plus 1, and then s sub n will be the sum of everything before it. Okay. Okay, so that's what we do. We just go through and kind of check these. This 1 over n, 1 over, so we probably want to start on this side and then work our way up. Okay, I sort of already know the answer. So anyways, our error, we need this less than 0.0001. So we need this less than 0.0001. So we start checking. This is obviously 0.25. That's not good enough. Whoops. So the first one, 0.25, is not good enough. Right? And then 1 over 7 times 2 is about 0.07. That's still not good enough. 1 over 10 times 3 factorial is about 0.016, so that's not good enough. Then 1 over 13 times 4 factorial is 0.0032, not good enough. 16 times 5 factorial, we get 0.0005, still not good enough. And then finally on this guy, we get 0.00007, which will put us in there. Right? So what I'm saying is that your answer then is everything before that last term. That thing right there is our S sub n that we want. So it's S sub 1, 2, 3, 4, 5, 6. Hence, the approximation is done with S sub 6, where S sub 6 obviously is equal to 1 minus 1/4 plus 1/14 minus 1/60 plus 1 all over whatever that is, 13 times 4 factorial, minus 1 over 16 times 5 factorial. And if you put that into a calculator, you could even do it by hand, you get 0.8075. Right? And that's it. That's chapter 9. Thanks a lot for watching. Bye-bye.